Buongiorno a tutti, good morning to everyone. And let me first thank the organizer for the very kind invitation, of which I'm truly honored. I will discuss some physics-informed method for spatial data analysis and for functional data analysis observed over non-standard support. In particular, we are interested in spatial and functional data that display non-Euclidean variation. And that non-Euclidean variation may be induced by... dovrebbe essere acceso. Ora mi sentite? No? Questo non funziona quindi? Devo usare un microfono gelato? Facciamo un'altra prova, mi sentite meglio? No? Ma se prendessi uno di questi? Il pezzo è meglio rispetto a prima, ma la voce è un po' davanti, forse basta dare un microfono. No, questo non c'è, questo è solo questo. Questo quindi lo tengo? Sì, sì. Ora è meglio? Parlo a alta voce. Allora, ricomincio da capo. Start from the beginning. We describe some physics-informed methods for spatial data analysis and for functional data analysis over non-standard supports. And in particular, we are interested in spatial and functional data that display non-Euclidean dependencies. Now, this non-Euclidean variation may be induced by the complex physics of the underlying phenomenon. I will briefly discuss an application to the study of blood flow within human carotids. It may be induced in the data by the presence of external driving forces that may lead to strong anisotropy and non-stationarities. Or else it might result from the non-trivial geometry of the domain over which the data, spatial or functional data, are observed. A domain that can be characterized by non-Euclidean features such as sharp concavities, holes, or a folded nature. For instance, in the bottom right picture, you can see neuroimaging signal observed and referred to neural activity over the cortical surface. The cortical surface is an highly folded two-dimensional manifold. And because of this highly convoluted nature, you can see that you observe data at locations that are very close in Euclidean distance, but they are far apart on the real anatomy of the domain. Again, here you can see forces exerted by blood flow over the wall of a carotid artery affected by an aneurysm. Or again, this is an engineering application, a design engineering application where we are studying pressure exerted by air over the winglet of a shuttle to optimize the shape of the winglet. The domain can also be a volume, again characterized by a very complicated shape. Let me see, well, the video doesn't work. With complicated external boundary as well as cavities. Okay. And it might as well be a linear network, such as a road network or a river network, on the top of which we observe the data that we would like to analyze. The class of models that I will present is by now pretty rich. It includes non-parametric and semi-parametric regression, generalized linear regression, intensity, density estimation, functional principal component analysis, functional partial least squares, and other methods. They are all built on a common building block that is a regression problem with a regularizing term that involves a partial differential equation defined over the domain of interest. All methods, the estimation problem, they are solved resorting to numerical analysis techniques such as finite element analysis or isogeometric analysis based on advanced spline basis. And everything is coded in an R C++ library that is available from CRAN. Now, before I start with the model, let me give credits to the many people that I was able to get involved in this line of research over the years, starting by the former student and junior collaborators. Eleonora Arnone was PhD and postdoctoral fellows in my department, and now is postdoctoral fellow of this department here in Padova. Laura Zimonti is currently at the Center of Artificial Intelligence in Lugano. Mara Bernardi is now at the Joint Research Center in Ispra. Brie Ettinger, now at Emory University. Federico Ferraccioli, who started collaborating with me when he was PhD student of this department, and now is at the Joint Research Center in Ispra. Eardi Lila, now at Southern University. Matteo Wilhelm, now at the Agroscope Research Center. And Christian Castiglioni, who is a current PhD student of this department. And moving to the collaborators, colleagues from my department or from other university, let me first thank the numerical analysts, Luca Formaggio, Luca Dedè, Fabio Nobili, and Simona Perotto. They are leading international experts in the numerical discretization of partial differential equation problems. And moving to the statistician, I should acknowledge the contribution of John Aston from Cambridge, Livio Finos from this university, Jim Ramsey, McGill, Alice Knipe, Bonn University, Piacere Secchi, my institution, Politecnico di Milano, and Mauro Bernardi, again from this department. Now, this is the essential form of the estimation problem that we consider. We have a d-dimensional domain D. This can be a non-convex, two-dimensional, three-dimensional domain. It can be a two-dimensional Riemannian manifold, a linear network. And in this domain, at location Pi, we observe a variable of interest, yi, and possibly also a vector of covariance, xi. And just to fix idea, let us consider this buoy zeta, where the yellow and red markers are location of buoys that carries devices that take measurement of oceanographic and atmospheric quantities, such as salinity of water, water temperature, concentration of various nutrients, temperature and humidity of air a few meters above sea level, wind speed, wind direction, and so on. And starting from the values observed in this location, we would like to estimate a map of the variable of interest, say water surface temperature, meanwhile accounting for the relationship and exploring the relationship with the area covariance. And we do it by a semi-parametric model where we model the mean of the response variable conditionally on the covariance and location through a possibly nonlinear link function with a semi-parametric regression with a parametric part and a non-parametric part that is defined as a function over the domain D. This function captures the spatial variation of the phenomenon under study. Now, to estimate beta and f, the two unknowns, we minimize a penalized loss function where the penalty involves the misfit with respect to a PDE that encodes the available problem-specific information about the phenomenon under study, a PDE defined over the domain D. Of course, data could be distributed across space and time. So let's say that we also have a temporal domain T, then the data location would be spatiotemporal data location, PITJ, where you observe a variable of interest and also covariates. And again, the model is as before. The only difference is that the function f is now defined over a spatiotemporal domain. And of course, the PDE is now a time-dependent PDE, or else we might use two regular Rosen terms that separately control the regularity of the field in space and in time. And of course, we can consider various missing data scenarios, sparse data, incomplete, spatially dependent functional data, as well as different sampling design. So the data could be observed over areal subdomain, over regions in space. They can be observed over intervals of time and various combinations of different sampling design. But I keep to the expression for space-only data because they are simpler. Okay, so let me discuss the key ingredients of this estimation problem, starting with the loss function. Of course, specifying different loss and link function, we can recover different modeling framework. So if the link is the linear and the loss is the least square, of course, we are in the framework of spatial linear regression, semi-parametric or non-parametric, depending on the presence or absence of covariates. If the loss is the canonical loss function, if the link is the canonical link function and the loss is the negative log likelihood, most appropriate for the problem at hand, then we are in the context of generalized spatial linear regression. We might also model, instead of the mean, we may model an alpha quantile with the loss being the quantile check function, in which case we are in the context of a spatial quantile regression. That is something that we are currently developing with Mauro Bernardi, Christian Castiglione, and Eleonora Arnone here in this department. And of course, you can, exploit the versatile framework of regression and further extend and generalize this model, for instance, including mixed effects. About the domain D, I already mentioned that this can be a complicated domain. Let me just give you the background literature. Now, the literature for data observed over two-dimensional manifold is mostly restricted to sphere-like manifolds, manifolds that can be represented by spherical coordinates. Of course, the type of application we deal with, they are out of this case. Outside of this specific case of spherical manifold, the literature is mostly restricted to smoothing methods and to space-only data. And for what concerns the literature for data observed in non-convex volume, then that is even scarcer. Essentially, there aren't available methods capable to analyze complex data observed in these non-trivial domains. Now, about the regularizing term, as I said, this is the misfit with respect to a PDE defined over the domain D, and that encodes our problem-specific information about the phenomenon of the study. This might come from the physics, mechanics, chemistry, morphology of the problem at hand. Now, PDEs are commonly used in most fields of sciences and engineering to model complex phenomena behavior. And here we use this PDE regularization to model space and space-time variation in a way that is directly suggested by our knowledge of the physics of the problem whenever we have a problem-specific knowledge. It is compliant with the shape of the domain, and it is extremely flexible. It naturally accounts for different forms of anisotropy and non-stationarity. To exemplify with linear second-order PDEs, for instance, with the second-order term, we may model diffusion effects with different directions and intensity of the anisotropy, and this direction and intensity may vary over space. With the transport term, we can model one-directional smoothing effects, again with different directions and intensity, and again, these directions and intensity may vary over space. With the reaction term, we may model shrinkage to zero of the solution, again varying over space. And with the forcing term, we have a further flexibility into the model. Just to illustrate, with the Boy data, of course, we can include our prior knowledge about the presence of the Gould stream. The Gould stream can be modeled as a diffusion advection problem, and thus modeled, it can be included into our estimator so that the estimator would know that the values observed in locations that are in the direction of the current are most strongly associated that the values observed in two locations that are in transversal direction with respect to the current. Now, to give you an idea of how powerful and versatile this idea is, I will briefly discuss a couple of applications. The first comes from the project Mathematics for Carotid Endarterectomy. It's a project that involved Politecnico di Milano together with Ospedale Maggiore Policlinico, that is the main hospital in Milano, to study the pathogenesis of atherosclerosis plaque, and in particular to investigate how the blood flow dynamics and the morphology of the vessel influence the onset and the progression of the plaque. Atherosclerosis is one leading cause of death in developed countries, as you know. Now, the data that we have are the patient-specific reconstruction of the common carotid artery obtained from magnetic resonance imaging. These are carotid artery affected by an high-grade stenosis, and we have blood flow dynamics measurement by echo-color Doppler at a section of the carotid located 2 centimeters prior to the bifurcation where the stenosis is. So now we have this measurement of the blood flow velocity at this cross-section of the carotid I'll zoom in the cross section, and these are the measurement of the blood flow velocity. And starting from this measurement, we would like to estimate the full time-dependent velocity field, because studying this field is important to study the pathogenesis of the stenosis. And of course, there is no way that classical methods can return physiological estimate, because this problem has a very complicated physics underlying, is the physics of viscous incompressible fluids. On the other hand, this physics can be used to define a partial differential equation that can be included into the estimation problem to obtain physiological estimates. Now, these physiological estimates, they are very important for the medical doctor because they highlight eccentricity and asymmetries of the fluxes that are crucial for this pathology. Moreover, they can be used as inflow conditions of fluid dynamical stimulation that mimic blood flow in the patient-specific anatomy of the carotid. And this is something that made the medical doctor enthusiastic, because in a not so far away future of personalized medicine, we could have an echo-color Doppler scan, which is a very non-invasive scanner. But the machine could have statistical and numerical methods built in, so that the medical doctor could evaluate what type of surgery is best for the specific subject under study. This is an altogether different application to the study of phone traffic data over the metropolitan area of Milano. This is a data set that was made available within a project, Green Moved, of which my colleagues Pier Cesare Secchi and Simone Vantini have worked a lot analyzing this data with altogether different techniques. More recently, we have started using also our method. So let me show you the data. The data are time-dependent, geo-referenced intensity of phone traffics. And for those of you who know Milan, of course, this is downtown. This is Linate Airport. This is the pavilion of the exposition in Rome. And these are the highways around Milano. So this is A1, and these are the east tangential, north and west tangential high-speed routes. And as you can see, the signal is highly affected by the texture of the domain, by the main road network. And the idea was then, so okay, this is the highway on the north of Milano. And as you can see, the signal follows very closely the highway because people phone as they drive, unfortunately. And the idea here was to use the texture of the domain, the road network, to inform the estimator. So in particular, we consider the main roads and derived an anisotropic, let me go back too quick, an anisotropic diffusion operator, which would say that the signal would diffuse more quickly along highways. And in this way, building this in this dimension problem, we were able to obtain an estimate that can account for the very strong anisotropy and non-stationarity in the signal. Of course, in this application, the PDE depends upon some unknown parameters that are estimated from the data. And in fact, even in contexts where we do not have any prior knowledge about the phenomenon in the study, this ability to estimate the parameters directly from the data is crucial because, for instance, we can estimate the anisotropy directly from the data. So in this application, we have a benchmark data set which concern rainfall measurement in Switzerland. And the rainfall, as you can see here, the size and the color of the marker is proportional to the rainfall. The rainfall display highly anisotropic behavior, which cannot be explained by elevation or by other covariates. In other ways, this can be learned from the data by letting the direction and the intensity of the diffusion tensor to be estimated directly from the data through profiling estimation techniques. In absence of any problem-specific information and in absence of any apparent anisotropy in the data, Then, of course, we would choose as a diffusion tensor the identity matrix, and we would penalize the estimation function with a simple isotropic and stationary diffusion operator, the Laplace or Laplace Beltrami operator, which simply measure the curvature of the function f over the domain over which it is defined. So this simple concept of smoothing is nevertheless compliant with the shape of the domain, because the differential operators are always defined over the domain of interest, which means that we will never artificially link data across concavities in the domain, but naturally the model will compute distances over the domain of interest, in the domain of interest. To wrap up, we have this beautiful estimation problem, which bonds together in this very happy marriage two of the richest and most powerful mathematical framework and statistical framework we have. The regression framework, maximum likelihood framework, that is probably the most versatile framework we have for the empirical model, and partial differential equation, the most powerful mathematical tool to model complex phenomena behavior. And thanks to a complex interplay of approaches and methods from statistics, from mathematics, both pure mathematics and applied mathematics, and from scientific computing, we are able to handle non-standard forms of spatial and functional data. And this is what we name physics-informed spatial and functional data analysis. Now we'll discuss about functional data analysis later on in my talk. Now, let me comment about the fact that, of course, you can interpret the regularizing term as a Bayesian prior on the function f. And of course, in that case, the smoothness parameter is giving the concentration of the prior around the solution to the differential equation. And of course, you might be familiar with many of the methods that have been proposed since the seminal work of Whittle back in the 1950s that link covariance operator to partial differential equation, and that has defined spatial data analysis techniques exploiting the implicitly or explicitly exploiting this link between partial differential equation and covariance operator. And of course, there are many similarities in what we do with respect to these other spatial data analysis techniques, such as state space model, Bayesian state space model, or the SPD approach made popular by INLA, by Harvard, Rue, and Finn Lindgren. However, there are also crucial differences, because here we do not leverage on any implicit nor explicit link between the PDE and a covariance operator. The way we use the PDE in the regularizing term make us let our hands free to choose any sort of PDEs such that the estimation problem is well posed. And these are PDEs defined over the complex domain that we are considering. So we are not restricted to the very specific types of PDEs, which are those that are linked to the covariance operator. Now, I will briefly give you an idea of the estimation problem in the simple case where we have a linear link. So we consider a linear semi-parametric regression where the response is modeled with this semi-parametric model with some additive noise that are independent with zero mean and finite variance. And we estimate beta and f minimizing a least square, penalized least square functional. Of course, this estimation problem is solved on an appropriate functional space, which is a Sobolev space of function with a boundary condition. And let me write the model in a matrix formulation. So while will be the vector of observed data location, f of n will be the vector evaluation of the field at the end data location, x will be the design matrix, H the at matrix in regression, and Q the matrix that project into the orthogonal complement of Rn with respect to the space spanned by the covariates. At this point, we can show that the estimator beta hat and half hat, which solve the estimation problem, exist they are unique. beta hat as a simple least square form. So design, transpose design to the -1 design data, minus the contribution, of course, of the non-parametric part of the model. The non-parametric part of the model, the F hat, satisfies this variational problem. This variational problem, unfortunately, it does not possess a closed form solution. So there is no way we can solve it analytically. And here we resolve two numerical analysis techniques. So the idea is that, of course, you approximate the infinite dimensional estimation problem to a finite dimensional estimation problem by introducing a suitable finite dimensional functional space. I will show you the discretization through finite element, which is the simplest to explain. So you start by partitioning the domain of interest into subdomains, for instance, by triangular meshes, and then you define some functional bases which span the space of functions that are globally continuous over the domain of interest and piecewise polynomial once restricted to any element of the mesh. So for instance, these are linear finite element bases. You have one such basis for each vertex of the mesh. And combining these bases linearly, you can obtain any function that is globally continuous and piecewise polynomial over the domain of interest. And of course, you can do it for three-dimensional domain as well as for linear network domains. Okay, so tau will be the mesh with no xi1, xk. D tau will be the discretized domain. F tau will be the finite element space. So it's the space of function globally continuous and polynomial. I will follow on with linear for simplicity. Polynomial once restricted to any element of the mesh. So C1, Ck will be the finite element basis which generate this space, which means that any function in this functional space can be written as a basis expansion using this basis. We can compute the matrix C, which packages the K basis evaluated at the n data location. We also need a few other finite element matrices. And finally, we are able to give you the form of the discrete estimator, the estimator that solves the discrete counterpart of the estimation problem. Beta hat is the one that we have already seen, and f hat is the function defined by this basis expansion whose coefficient has this expression. And this expression is the simple expression of a penalized regression estimator. So psi, of course, here plays the role of the design matrix for the non-parametric part of the model. So we have design, transpose design, plus lambda penalty. This p discretizes the penalty term to the -1 design transpose data minus the contribution of the parametric part of the model. So in the end, after we have made such an effort, we have some estimators that have a very simple form, of which in statistics we are extremely familiar. There is a lot of literature, decades of research on estimators that have this form. And then you can, of course, start wondering about, for instance, the properties of the bias and the variances of this estimator. And in fact, since we were ambitious, we did not just study the convergence of this term for the discrete estimator, but we made a step back and considered the infinite dimensional estimator. So the estimator that is the solution to the infinite dimensional estimation problem. This cannot characterize analytic, as I said. With Eleonora Arnone, Fabio Nobile, and Alois Knaip, we consider a simple, a purely non-parametric model. So F hat solves this penalized least square functional. And before discretization, we studied the rate of convergence of the bias of the estimator and the variance of the estimator under suitable functional norms. And this led to the proof of the consistency of the estimator. And in fact, we were able to prove that the estimator, the mean square error of the estimator achieves the optimal rate of convergence for non-parametric estimators, where of course the rate of convergence depends on the regularity of the true unknown f. considering the discrete estimator, so after discretization, and considering a mesh that diverges together with the observation, then we studied again the rate of convergence of the bias and the variance in a discrete norm at the data location, proving the consistency of the estimator and proving again that their mean square error achieves the optimal rate of convergence for non-parametric estimator. With Federico Ferraccioli and Livio Finos, we considered the semi-parametric model, but making the simplifying hypothesis that the mesh was fixed. And we were able to prove the asymptotic normality of the estimator f hat and of the estimator beta hat. And of course, this asymptotic normality could justify the use of Val-type inference on beta and half. However, this asymptotic inference may be severely under-conservative. And of course, we attempted all the various corrections, over-smoothing, under-smoothing approaches that have been proposed over, I don't know, 50 years for simpler semi-parametric and non-parametric regression models, but none of these gave a truly satisfactory answer. And for this reason, more recently, we have been exploring some non-resampling ideas proposed by Finos with co-authors in more standard regression settings that has to do with side-flipping of the scores of the models. And we coupled this with a study of the spectral properties of the residuality matrix lambda associated with the non-parametric part of the model. I've done something I shouldn't do. And this led to the definition of Eigensign flip statistics. I will not enter into the detail, but based on this statistic, we can define asymptotically exact test on beta. And in fact, not only the test is asymptotically exact, but also it proves to have a very good control of type 1 error in small sample scenarios, differently from all other alternatives based on more classical approaches. Currently, we are further extending this very fascinating line of research, and we have some promising preliminary results on inference on F. And this line of research is particularly interesting because, in fact, this approach that we have here devised for our methods is, in fact, valid for a vast class of semi-parametric and non-parametric regression model based on splines, smoothing splines, multivariate splines, nimble splines that are extensively used in applications. Now, so far, I have discussed a spatial regression problem. Now I will move to density intensity estimation problems. That is another type of problem that are often encountered in spatial data analysis. So in this case, the data are locations of events, and we would like to estimate the intensity, the density, the unknown density of these occurrences, or the intensity of an inhomogeneous Poisson process that has generated such occurrences. And of course, we would like to do it in a way to respect the shape of the domain whenever the domain influences the phenomenon under study. Here we are seeing an application to the study of criminality in the city of Portland, and the city of Portland is divided into half by a river, the Willamette River. And as you can see, there is an high criminality on one part of the domain, which is not matched by an high criminality on the other side. So somehow the river plays the role of a physical barrier here to the diffusion of the phenomenon under study. If while n are independent realization from an unknown density h defined over the domain D, and we consider the log density f, then we can estimate f minimizing this penalized log likelihood function. And again, we were able to prove that the estimation problem is well posed and that the estimator is consistent, this time in a symmetrized Kullback-Leibler distance. And of course, this can be taken to the various sorts of domains that have been discussed, manifold domains. Here is an application to the study of the intensity of earthquake over the globe, to road network, linear network. Here is an application to the study of the density of crimes over the roads of Chicago. And again, it can be taken to space-time, so estimating densities of events occurring over space and time. In the last part of the talk, I will mention methods for functional data analysis. So let's say that now we have a data set of functional signal observed over multidimensional complicated domain. So let's say that I have a neuroimaging scan for myself, for Eleonora Arnone, for Federico Ferraccioli, Mauro Bernardi, Cristian Castiglione, and Livio Finos, and they will forgive me for putting the picture on my slide. So now I want to explore, for instance, the variability of these functional data. I want to solve a functional partially square problem. How can we do it? In the unifying framework that I described before. So I have n statistical units. Each of them is a noisy and discrete evaluation of a functional datum defined over the domain D. So Xij will be the value observed for the ith statistical unit at the location Pij. So this could be the observation in one location of my of a neuroimaging scan for myself. And we might also have some other variable associated to the statistical units. And again, we consider the same type of estimation problem that I was presenting before. So it's a penalized loss functional. And again, depending on the loss function, we are able to define different functional data analysis methods. So for instance, you can define functional partially square. You can define functional principal component analysis. I will discuss this last one in more detail, in which case the loss take the form of a rank 1 approximation to a principal component analysis problem. In particular, you estimate sequentially the principal component and the associated score, minimizing this least square function. Now I will conclude with the application. Unfortunately, I don't have the scans of myself or Livio Finos or Federico Ferraccioli, so on. So we will have to do with some publicly available data set, which involves schizophrenic and healthy subjects. Now we consider functional magnetic resonance imaging signal. This fMRI takes a measurement of an hemodynamical signal that is related to the ratio of oxygenated and deoxygenated hemoglobin. Now, since cells activation requires oxygen consumption, this signal can be taken as a proxy of neural activity, of cell activity, in particular neural activity. And the signal is referred to, let's see if the video works, let me go back. The data is referred to the gray matter, and the gray matter is a volume that has a very complicated shape with complicated external boundaries and cavities. And of course, most neuroimaging analysis today, they are based on methods that rely on the Euclidean distance. And unfortunately, this is not the best we could do. And there is a growing awareness of the need to include more and more of our knowledge also of the anatomy of the brain to advance our still limited knowledge of how the brain works. And in that respect, our method are some first instances of methods that comply with the shape, with the anatomy of the organ. We consider some task-based fMRI. In particular, the subject, while they do the scan, they are asked to play a video game in which they virtually inflate a balloon. The larger the balloon, the more is the reward they can get for that balloon. At any time, they may cash out the reward and start inflating a new balloon. Of course, if the balloon explodes during inflation, for that balloon, they are not going to get any reward. And they play continuously over the time, the 12 minutes of the scan. And at the end, they were given the amount in dollars they had collected through the video game, which was in the under of a few hundred bucks. So there was quite an active involvement of the subjects in this study. Of course, these are studies that are conducted in the USA because we don't have the money for doing that. Okay, anyway. Now, we are using this task, we are considering this task because schizophrenic subjects, they have been reported in the literature to be more risk adverse to healthy subjects. And somehow we would like to explore their neural activity as they are involved in a task that involves some risk appraisal and decision making of type go, no go. In particular, we compute here functional connectivity with respect to a region of the brain, the left anterior singular gyrus, which is a key region involved in risk appraisal during decision making and in loss aversion. And overall, of course, our ultimate goal would be to see if there are differences in what happens in the brain of schizophrenic with what happens in the brain of healthy subjects as they do this video game. Now, these are the principal components obtained with the technique I briefly mentioned before. So this is a view of the principal component first, second, and third on the cortical surface. And on the top is a view within the gray matter. We are slicing through the brain. And these principal components, they all have physiological interpretation. So this is a project conducted together with the Vesta Neurological Hospital. It's one of the major neurological hospitals in Italy. So for instance, the first principal component displays greater variation in the inferior frontal gyrus, which is a region implicated in no-go task and in risk aversion. Now, if we look at the score, it is amazing to see that there are sharp differences between schizophrenic and healthy subjects. And in fact, even a simple linear discriminant analysis can very well tell the schizophrenic from the healthy subjects with very few mistakes. If we were to use the best state-of-the-art techniques, so for instance, the so-called pre-smoothing approach in functional data analysis, then we would find somehow high accuracy and precision. But the true schizophrenic would be predicted more or less half and half healthy and schizophrenic. So not such a good result in terms of discrimination. So this method can truly support advances in forefront fields of application. Now, we have implemented all methods with a particular care to computing efficiency and computing sustainability, with an idea of being able to tackle massive data analysis problems. And for this reason, the methods implement techniques from numerical linear algebra, stochastic approximation. To give an idea of the dimensionality of the estimation problem we just seen, there we had about 200 subjects. For each of them, the functional data, the functional datum was an array of 30,000 entries. The estimation problem has an execution time that is a fraction of a second. And I did not discuss comparison with other methods, but we have carried out extensive simulation studies to compare our proposal to best state-of-the-art techniques from spatial data analysis, from functional data analysis, whenever competing techniques were available. And we highlighted the comparative advantages of the proposed method. And moreover, as I said, the methods are really capable to tackle challenging data analysis problems and might be the support for significant advances in forefront fields of application. Now, this has only been possible through a very strong synergies of various approaches from different scientific disciplines with a very intense interplay of statistics, mathematics, scientific computing, and domain knowledge. Today, we are here to celebrate the success of a department and even before of a university that has a long history and that has been the cradle for statistics in Italy. And I believe we must do it with an eye of what lies in front of us to the future centuries. And multidisciplinary approaches are certainly of paramount importance to tackle the many challenges that will be posed us by the analysis of increasingly complex data and help us develop statistical methods and models capable to support our community in the advancement of the understanding of this complex world. Thank you for your attention. Lascio la parola ai discussant.
Thank you very much for your inspiring speech. Very interesting. I'd like to introduce to discuss Professor Ilaria Prosdocemi, Department of Environmental Sciences, Informatics and Statistics, Ca' Foscari University of Venice. Professor Antonio Calcani, Department of Development, Psychology and Socialization, University of Padua.
Hello, everybody. Hope you can hear me. I have to say that Laura stole my thunder a bit in some of the comments that I have, but hopefully. So first of all, I want to thank, of course, the organizers of the event and Laura for her very interesting talk. I forgot to bring my timer. I'll try to put the timer. It's fine. Okay. So indeed, it is a great pleasure to be here to do this brief discussion. So as Laura already mentioned, I will. Her work has many similarities with works of others, and I'll point out the ones that I know a very tiny bit about. Of course, it has a lot to do with the very popular framework of generalized additive models. In particular, I picked out, I think, the most maybe famous ways in which these approaches are implemented. Of course, the MGCV package that implements all the work of Simon Wood, and the Bayesian perspective of GAMS, which go under the name of structure additive distributional regression models, as implemented in these packages. And of course, it's a very busy landscape, the generalized additive model landscape. Gamma's boosting all sorts of things. And the other, the other type of work that of course, is as Laura already mentioned, the other work on which I found some similarities is possibly the latent Gaussian models expressed as Markov random fields, Gaussian Markov random fields in the work of Harvard Rue and the R in Latin. One of the things that I think would have this type of models have in common, this type of implementations have in common, is of course the smart use of numerical methods, which Laura has very clearly demonstrated is something that is necessary to make these methods usable to users, and the use of the development of very stable and usable software. And arguably, I think the MGCV and R INLA packages are so popular and so applied by people partially because they have very usable software and very well-written documentation. So this is something there is something to be said about advertisements in popularity gained by just usability of software, I think that. So as Laura very clearly explained, her work rotates around the problem of penalizing things and penalized estimation or penalized regression estimation. So why would we want to do a penalty? Why would we want to maximize this penalized likelihood? Well, there is various frameworks that rely on the use of penalized likelihood. Of course, there is all the type of problems in which we want to regularize our estimation. And this led to very famous penalized regression frameworks such as lasso, ridge regression, which also is known as Tikhonov regularization, elastic net, all sorts of things. Of course, another way in which we can look at penalization is that it can simply be a way in which we want to put some constraints on some properties of our estimation, for example, the smoothness of functions. This is very tightly connected to the idea of that we might want to set a prior on our parameters, for example, in a Bayesian GAMS, Or, as Laura clearly explained, this penalization could come from the idea that we might want to include some physics-informed properties of the problem. And one of the questions that I have when I look at all these different approaches and how they present the different ways in which they get to essentially that form of a loss function, and this term is maximizing a loss function minus a penalty, or minimizing the negative loss function and a penalty. But aren't these all sort of the same things? And one of the things that when I was reading Laura's work, one of the things that sort of immediately popped to my mind was that, well, clearly there is, as this penalty term encapsulates understanding of the physics, and that the term has been used of prior information on the problem. And of course, when I hear the word prior information, what I ask is, isn't this, could we not turn this into a Bayesian prior? Could we turn all this very fancy modeling of the various diffusion terms and reaction terms and all of that into Bayesian prior? And why would I think that this could be of interest? Well, because when we are being Bayesian, we can also be a bit more informative on whether we have a clear understanding of the physics or a weak understanding of the physics. I think all the examples Laura gave us were very sort of convincing, and surely fluid mechanics is something that we understand pretty well. But I wonder if there are some situations in which our understanding, or how well we understand really the problem, the physics of the problem is, it could be useful to be able to specify how well we understand all the actual constraints that we're setting. And in this also line of thought, of course, there is a lot of work done in the Bayesian world about prior elicitation and how to indeed discuss with practitioners and people who understand the problem, and trying to characterize, okay, that how to translate our understanding of a problem into, in the Bayesian world, in a prior, but in Laura's world, we'll be needing to translate our understanding of the problem into this type of matrices and vectors and constants. And I wonder how much, you know, a user of a method rather than a developer of a method will be able to express their understanding of the problem into PDEs. Of course, maybe if we're talking to engineers, they might at least know what a PDE is, but in some other applications, I can see that it might be complicated to elicit or to ask the user, well, can you please give me some information about all these matrices? So I think there is an interesting, something maybe that can be discussed about how can we, how do we derive all these terms when we are a bit unsure about the physics, or when the person that is doing the application cannot express themselves in the terms that are used by the by PDEs and by mathematics. Indeed, another point that Laura made was that, of course, there is some similarities. We can retrieve very the typical models, the models, for example, of IID, isotropic spatial regression, can be found back with specific types of certain type of cases of the values of K, D, and C. And my question for her, but maybe it's probably written in some of the papers, but I just couldn't read them all, is if there is more to be said about what types of spatial models can be retrieved with some special types of these special cases of these terms. And in particular, because I wonder if this could be helpful, and this goes back to advertisement for the SRPDE approach, on what do we lose if we don't use, what do we lose if we don't use these fancier methods and understanding of the physics of the problem? So in some sense, can we use these approaches? Could we quantify what we lose by not exploiting the physics of the problem in some mathematical terms? And lastly, I have a small point to make on, of course, there is I think in generalized additive models work, which is the work that the part of this world that I know a bit better. Of course, there is lots of work in trying to quantify uncertainty. If anything, I think uncertainty, of course, there is this asymptotics result, and this we can compute with this, as you said, with this. There's a lot of work done on estimators that can be expressed as linear combinations of matrices and data. But there is, I think, an increasing understanding that there is, whenever we do this type of approximation, uncertainties can come from different sources. And I wonder if there is an understanding of the uncertainty that comes from the discretization step, and how could we include that in the characterization of uncertainty in the SR-PDE approach. And on a last, more happy note, I think this type of application is very interesting to see, and I think one of the great selling points of this type of approach, of the SR-PDE approach, is of course that it's been developed with applications in mind. It's application first, and it's very much informed by application. This is of course a theme that I think will come back into this conference, I hope. And this is something, of course, that is to be, I think, sought more by the whole statistical community. Similarly, also, I think we need to embrace the fact that we probably will need to talk a bit more in our lives with the methods, with our colleagues from the Department of Mathematics, Engineering, Social Sciences, Medical Sciences, and so forth, because in the future, statistics is just going to be one of the methods present to solve problems, and we'll need to exploit all the knowledge that is possible to gain from different fields, really, to be able to go forward with our understanding of the world. So I very welcome this type of contributions to these challenges. So thank you very much, and I will.
Okay, I would also like to thank you, the organizers, for for giving me the opportunity to act as a discussant of your valuable research work, Laura. And okay, of course, the main point of your work, as far as I have understood, is to model the spatial complexity or the non-Euclidean properties of the spatial domains. And the main idea is to include all the information about the spatial domain by using a partial differential equation modeling. And of course, with some boundary conditions. As you have said now, what I'm doing, okay. Of course, no, they are going. As you have said, Laura, the spatial information is included in the partial differential equation, and of course the diffusion term is what tells something about the anisotropy of the domain, which is of course as far as I see, as far as I think, the key one of the key property of this kind of problem. And the solution which underlie the solution for estimating the f function includes the information about the spatial domain. And of course, as you have shown, the estimator includes, of course, the diffusion term, the discretization C, and so on. So my question is, from a statistical point of view, my first question is, how could we, you have said something in your presentation, but how could we make a data-informed estimation of this kind of prior information, and how those informations affect the bias variance trade-off, for instance, or how those informations affect the flexibility of the model to predict new data, for instance. Then, by reading your available work, I have thought that there might be some cases where, for instance, the researchers have little information about the data, or there are some partial information about the boundary conditions or the boundary of the spatial domains. And it came in my mind something about the the spatial fuzziness or fuzzy spatial data. For instance, there are few examples where, I don't know, where we are going to model, for instance, two seas that they overlap, or some brain areas that they are overlapped in some regions. For instance, there are some cases where we have little information about the differences between memory and learning processes, if they share the same neural network community or something like that. And in all these cases, I was thinking, how could we use your method in order to include this kind of partial, let's say, information, or this kind of fuzzy information, as many scholars said. Just to highlight that, I think that by using your method, for instance, we could include, okay, in the first case, we could use fuzzy information or fuzzy data could be included as data. And of course, there will be another estimation problem. But in the other case, the flexibility of using partial differential equations with those kind of boundary conditions could help researchers working in fuzzy statistics, for instance, to include fuzzy boundaries as in the penalizing term, by including, for instance, by modeling the boundaries by using fuzzy partial differential equations. I was just thinking about these kind of insights that I had by reading your work. And that's it. I think I was fast.
So, thank you very much. I suppose there could be several questions from the audience, but I think that Laura needs to answer a lot of questions about discussion. So this is the next one.
Penso di sì. Grazie.
No, ma non penso che lo userò. So let me first of all thank the discussant for these comments, insightful comments, and lots of fascinating suggestions of future research. There were many comments, so yeah. I will give a short answers. Links with other approaches. Now, there are classical studies, for instance, made by Grace Waba and Auknichka, that in the very simple context of univariate smoothing splines, they analytically and explicitly describe the link between non-parametric regression and Bayesian models, as well as Kriging, for instance. Now, unfortunately, we cannot do the same, because in our case, the regularization terms that we are considering, so let me share. Sono uscita. Ok, I cannot. Sono uscita dalla riunione. No, no, too difficult. Posso vedere le slide di Carlo? Grazie, magari la pagina indietro, vediamo ancora indietro, un altro ancora, boom, così va benissimo. So unfortunately, in our case, the partial differential equation that we consider and the domain that we consider are such that we cannot characterize analytically the green function in the kernel of the operator that we use in the penalty term. which means that unfortunately we cannot explicitly explore those links for our model. However, this is also a plus in the sense that, of course, we can consider, as I said, general forms of partial differential equation and general forms of domain, and our only constraint is that the estimation problem is well posed. And this, as I mentioned earlier on, lets our hands free to model types of spatial and spatio-temporal variation that are not encodable in one of the concepts, covariance operator, Gaussian fields, that we typically work with in statistics. Of course, the PDE regularization requires, when we really want to use the prior knowledge, requires strict collaboration with domain experts. And of course, it must not be a perfect description of the phenomenon in the study. For instance, in the application I show you to the fluid dynamics within the blood, we have very advanced model, Navier-Stokes equation, but we are not using that complicated model. We are using simplified model that nevertheless built into the models our knowledge about the expected shape of the velocity field. And of course, those are specified, as I said, apart. So they include some parameters that are estimated from the data. And also we can, with the smoothness parameter, learn how much the physics is really a good description of the phenomenon, because the smoothness parameter lambda is typically selected in cross-validation, generalized cross-validation, and this naturally adjusts for how good the regularity term is. Now, it would be extremely fascinating to explore inference approaches that account for the uncertainty, for instance, in the definition of lambda. What we have started doing so far is for a fixed smoothness parameter. But certainly this is something that we want to do, and we must do. I will maybe move to the discussion by Carlo to say that it talks about fuzziness in the data allocation, fuzziness in the domain, fuzziness in the boundary condition. And in fact, this is extremely interesting because in the application that I showed you, in most of the cases, the domain itself is the result of some measurement, some segmentation of medical imaging and so on. So in fact, in many applications, the domain itself is known with uncertainty. And that would be truly a fascinating line of research. We said it many times, we haven't tried any attempt yet, but it would be somehow fascinating to combine the idea of analyzing this complicated data on the top of a domain, a manifold, which might be unknown itself to some extent. So I thank you for your discussion.
Other questions for Maria Sangalli? So, Maria Sangalli,
I would opt for the second. Okay, Lisa.
Curiosity about the and the meaning of the first principal component, which is not associated with in a diagram. Did you have a chance to explore what that is, what that represents?
No. So we have seen that it's somehow related to so it's related to areas that are connected to somehow loss aversion, at least in the literature. In fact, the fact that the first principal component is not associated with a phenotype is something that we have seen also in other studies that we have conducted, comparing other cohort of subjects.
So I cannot give you a precise answer, but it's true that we often see the differences between pathological and healthy individual in the subsequent principal components. Because the first component try to somehow get a grand mean effect. And this grand mean effect is probably some behavior that is somehow common to healthy and pathological. Thank you.